Hi class, welcome back to thermodynamics. At the end of last lecture, we derived the TDS equation. So what we were doing is we were assuming that we had a pure, simple, compressible system. Okay, a pure substance in a simple, compressible system. And so we can say that heat transfer for an internally reversible process. And remember, we use the Clausius inequality to determine whether or not a process is reversible, irreversible, or impossible. And so the heat transfer for an internally reversible process is going to be the integral from state 1 to state 2 of temperature times the change in entropy, TDS. And this process is path independent. So it doesn't matter how you get from state 1 to state 2. It's just the endpoints that matter in this case. So state 1 and state 2. So in this case, we'll be doing temperature. If we integrate, we'll get temperature times the difference between the entropy at state 2 minus the entropy at state 1. And that'll give us the heat transfer for an internally reversible process. And this piece right here, this internally reversible piece, so this tells us this equation is applicable for ds equal to 0, which tells us that heat transfer is then equal to 0. So remember, the assumptions built in is that we have, this is for a simple, compressible, system and a pure substance. So what does it mean when a system is compressible? Well, that means we can have a process by which we can change the density of the substance between state 1 and state 2 following a change in pressure. So if pressure changes from state 1 to state 2 for a compressible system, the specific volume or the density will change along with it. And so the TDS equations that we derived for under these assumptions were that TDS is equal to the change in internal energy plus PdV, pressure times the change in volume. Okay, so this would be for constant pressure process. And the other one would be that TDS is equal to dH, so change in enthalpy, minus V, so constant volume process, times the change in pressure. So why do we care? Well, recognizing these relations here will help us solve some problems if we do not readily have entropy data available. So now let's move on and look at some assumptions for an incompressible substance. So let's start with the built-in assumptions. So for an incompressible substance, we have the specific volume throughout a process is going to be constant, right? We're not changing the specific volume. We're not changing the density because the substance is not compressible. So this is not going to change throughout the process. And also, then, in that case, specific internal energy is only going to be a function of temperature. So it's a function of temperature only. So this tells us that du is equal to C, which is a function of temperature, dt. So remember, C is the specific heat capacity of the substance. And for an incompressible substance, C for a constant pressure process, Cp, is equal to C for a constant volume process. So it depends on the substance, and it's a function of only temperature for an incompressible substance. So now let us return to those TdS equations from earlier. So we had T ds is equal to du plus P dV. Okay, well, here's the thing. If we have an incompressible substance, the specific volume is not changing. So let me change the color. So dV is 0. That's not changing, which means that TdS is going to be equal to du in this case. So to simplify, that means that ds, the change in entropy, is going to be equal to the change in specific internal energy divided by temperature, which, as above, we said that du is equal to the heat capacity, the specific heat capacity times the change in temperature. Then we're going to have that du over T is equal to C, which is a function of temperature, dt over T. So for an incompressible substance, we can get ds just by knowing the two temperatures, the start temperature and the end temperature for the process. So that means, if we keep moving on, that delta S so delta is just being the overall change for the process, is going to be equal to the integral from the initial temperature to the final temperature of the specific specific heat capacity, which is a function of temperature. So we can look that up. dt over T. So if we integrate, say, dt over T, the C is a constant, although it is dependent on temperature. Well, we have 1 over T dt times C. And so when we integrate that, we get C times the natural log of T2 over T1. And this is when C is constant. And there are different ways we can model this. We could model it by taking the average temperature for the process, for example, and we can look up C in your textbook in table A19. Okay, so I'm just going to highlight our final equation right here. I'm going to put a big box around it. Okay, so this is what we were getting at. Okay, so this is very important. Okay, so now let us try an exercise together from the book. This is number 15 in chapter 6. And we have 1 kilogram of water contained in a piston cylinder assembly, initially at 160 degrees Celsius and 150 kilopascals. It undergoes an isothermal compression process to saturated liquid. For the process, work is equal to minus 471.5 kilojoules. And so we need to determine for the process the heat transfer in kilojoules, and B, the change in entropy in kilojoules per kilogram. And we want to show the process on a sketch of the TS diagram. So let us begin with just jotting down our givens. So we were given that T1 is 160 degrees Celsius, and P1 is 150 kilopascals, which is the same as 1.5 bar. Okay, and we are told that the process undergoes isothermal compression. So with compression, we know that P2 is going to be greater than P1, but isothermal tells us we have constant temperature, so T1 is going to equal T2, which is going to be 160. And it undergoes the isothermal compression to a saturated liquid. So that tells us we're on the far left side of the vapor dome, where our quality, so X2, is going to be 0 because we're at a saturated liquid. Remember, saturated gas tells us that quality is 1. All right, so now let's just start by sketching this on the TS diagram to have a sense of where we are. So TS diagram, remember, is temperature versus entropy. And so we'll just do degrees Celsius, and we'll just do a specific entropy in this case. So it'd be kilojoules per kilogram Kelvin. Okay. And so we know that the vapor dome is going to be important. So I'm just going to draw that on. And it's easy enough to know where we end. So we're going to end at 160 degrees Celsius. Right on the vapor dome for saturated liquid. So this is 2. This is where we end. And now let's just double check to see where we begin. So whether we begin somewhere in the vapor dome or outside of it. So we're told that temperature is 160 degrees Celsius and pressure is 150 kilopascals. So I'm just going to open up our tables. And here I'm at table A4. And so this is the properties of superheated water. And so let's just see if we're outside the vapor dome. And so for pressure of 1.5 bar, yes, if we have temperature of 160 degrees, we are in fact superheated. So we are going to start somewhere out here. And this is a constant temperature process. Okay, so check, we did this. We showed our process on a TS diagram. Now we can go ahead and we can even look up entropy if we wanted to, because we know that's going to be important. But first, let's just start by, oh yes, we're already also given work. So work is minus 471.5 kilojoules. So for A, we want to find the heat transfer. So we want to find Q. So A, we want to find Q. And B, we want to find delta S. So let us begin with Q. And we're just dealing with water, 1 kilogram of water in a piston cylinder assembly. So we have a piston cylinder assembly. It's undergoing some process. Well, it's undergoing compression from 1 to 2. And we have 1 kilogram of H2O. Okay, so 1 and then 2, we're undergoing compression. So this would be 2. So we should start with, of course, the first law of thermodynamics, and that would be with an energy balance. So I'm going to open up a new page for that. So this is still 6.15. So let's go through the solution. So for this process, we're going to have Q minus W is equal to mass. So we don't have, this is a control mass problem. So we're going to be dealing with internal energy, not change in enthalpy. And the other thing is we can ignore kinetic and potential energy effects. So we just are looking at the change in internal energy. So Q minus W is equal to M U2 minus U1. So we're given W, and we can go ahead and we can solve for Q. Q is going to equal M times U2 minus U1 plus W. And now we can just look up U2 and U1 in our tables. So U1 for 160 is going to be 2,595.2 kilojoules per kilogram. And if we wanted to just add in our entropy to our TS diagram, we could too, now that we have the tables opened. So S1 is going to be 7.4665 kilojoules per kilogram Kelvin. So this is going to be 7.4665. So now let's go ahead and look up U2. So now we know we're under the vapor dome, so we're in the liquid vapor tables. And we know that the temperature is still going to be 160, so let's find 160. And so it's a little difficult to see on here. So just remember, so for internal energy, under the vapor dome, we're given saturated liquid, saturated vapor. We know that X is 0, so we are at a saturated liquid, so we'll be in this column right here. And for entropy, we'll be in this column over here. So 160 for specific internal energy, we're going to be at 674.86. And for our entropy, we're going to be at 1.9427 kilojoules per kilogram Kelvin. So for U2, we have 674.86 kilojoules per kilogram. And for S, we have 1.9427. Okay. So we're almost there. Now we just have to plug in. We have everything we need. So Q going to be, we had 1 kilogram of water times 674.86 minus 2595.2 kilojoules per kilogram. W was minus 471.5 kilojoules. And so we end up with Q equal to minus 2,391.8 kilojoules. And finally, let's just find delta S. So delta S make sure I was clear. So kilojoules per kilogram. This is a capital S here. So extensive property. So delta S is going to equal M times the specific entropy at our final state minus the specific entropy at our initial. So this is going to be equal to 1 kilogram times 1.9427 minus 7.4665 kilojoules per kilogram Kelvin. So delta S is going to be 5.5238 kilojoules Kelvin. Okay, so that was it with that one. Now, let's just explore what would have happened if we applied the incompressible model here. Okay, so let's just try it. So delta S is equal to C times the natural log of T2 over T1 for the incompressible model. So we had a temperature of 160 degrees Celsius. So that's pretty close to 400 Kelvin. So let's just look up C for water at 400 Kelvin. All right, so I'm in our tables. And so you want to find C. So we're going to be at specific heats. Scrolling. There we go. So for water at 400 Kelvin, we have 4.256 kilojoules per kilogram Kelvin for C. So this is going to be 4.256 kilojoules per kilogram Kelvin times the natural log of T2 over T1, and T2 was equal to T1 because it was an isothermal process, and so that means that T2 over T1 is going to be 1. So we're going to have the natural log of 1, and so that's going to tell us that delta S is 0. So this does not apply. We cannot use the incompressible model on problem 6.15, because we're not dealing with an incompressible substance. We are compressing a substance in a piston cylinder assembly under constant temperature. So it just does not apply. It does not make sense that we would not have a change in entropy for that process. So looking back, our change in entropy was 5.5238 kilojoules per kilogram Kelvin. So it does not apply. To our problem 6.15. Well, one, because we're not dealing with a liquid. We're going from a gas to a saturated liquid. So it's not a liquid throughout the whole thing. V, specific volume, is not constant. And also, internal energy is a function of both pressure and temperature, because we start as a vapor. All right, so we cannot apply the incompressible model to our problem 6.15, but let's do an example in which we can apply that model. So let's try again. So let's say that T initial is 160 degrees Celsius, which is 433 Kelvin. And we're still dealing with 1 kilogram of water. However, our initial pressure is 8 bar. So if we go back to water here, our tables for water. So if we have a temperature of 160 degrees Celsius, then to be within the vapor dome, our pressure has to be at most 6.178 bar. So we are to the left of the vapor dome. So we're dealing with a liquid here, which may be modeled as an incompressible, substance. So the incompressible model will work on this problem. And let's say that the total initial volume is equal to the total final volume, which is going to be 3 cubic meters. And then this is not going to be an isothermal process. T2 is going to be 100 degrees Celsius, and that's going to be the same as 373 Kelvin, and P2 is going to be 12 bar. Okay, so we can find delta S just by using this relation up here for the incompressible model. So 373 and 400 Kelvin, well, 433 Kelvin. 400 Kelvin is right in the middle, though. So we can still use this value that we looked up for C earlier in our tables. So delta S is going to be 4.256 kilojoule per kilogram Kelvin times the natural log. And this ratio in this natural log for temperature, remember, this is the absolute temperature scale. So if we're dealing with metric, it has to be in Kelvin. And if we're dealing with English units, it has to be in degrees Rankine. So this is going to be 373K over 433K. And this is going to give us minus 0.6348 kilojoules per kilogram Kelvin. And for 1 kilogram of water, it would just be minus 0.6348 kilojoule per Kelvin. And it just occurred to me that in our last example, we're missing a minus sign here. Okay. All right. So next up, actually, let's calculate this one more way too. So we could use this incompressible substance model, and we could also look up S1 and S2 using table A2. So S1 is going to be approximately the entropy for X equals 0 for a saturated liquid in our liquid vapor tables for 160 degrees C. And S2 is going to be, can be approximated by using those tables for the liquid vapor for under the vapor dome for water at 100 degrees C. So just as a function of temperature here. And so looking these up in the tables, you'd get 1.9427 kilojoules per kilogram Kelvin at 160 degrees C. And in the tables, you'll get 1.3069 kilojoules per kilogram Kelvin. And so if you take the difference, if you take 1.3069 minus 1.9427, you get delta S equal to minus 0.6358 kilojoules per kilogram Kelvin. So you get pretty close. So you could approach this problem either way. Now let's move on to ideal gases. So remember, the ideal gas law should be completely burned into your brain at this point, and that is PV equals RT. Right, for our gas. R being for the gas, that's not the constant, this is gas specific. That's not the universal with the bar on top. So, change in specific internal energy. Let's model that with, that can be modeled from CV, which is a function of T. So specific heat capacity for a constant volume process, dt, that gives us du. And dH can be modeled using Cp, so for a constant pressure process, as a function of T, dt. Okay, so we were using this before. Now, let's relate this to change in entropy. So ds is going to equal du over T plus P over T dV. And these are all lowercase because we're dealing with specific quantities. So where did this come from? Well, this was our TDS relation that we started the lecture with. TDS is equal to du plus PdV. That's all that is. And I just divided each through by T. And similarly, we can do the same thing with dH. So TDS, so I'm going to divide through by T. So ds is equal to dH over T minus V over T dP. Okay, so let's keep going. Now, let's see. Let's plug in CVT dt for du. That'll be our next step. So ds is going to equal CV, which is a function of T, dt divided by T, plus, now what I'm going to do is for P over T, we know that P over T is going to equal R over V using the ideal gas law. So now this is going to equal R dV over V. All right, so what am I doing here? Well, I am trying to get like terms together so I can integrate. So in this case, before we had d over t. Well, we have mixed variables. That's not going to be nice to integrate. So now what we did is we subbed in for du cv dt. So we have dt over t. Yeah, we can integrate that. We have 1 over t dt, basically a constant over t dt t. Constant over t dt. There we go. And here what we did is said, well, now we're also mixed. We have some p's, which is variable. We have t, which is variable. And we're changing specific volume. Oh gosh, that's a mess. So what we did is, well, r is going to be a constant. And so now we can integrate dv over v. We're just trying to simplify here. And now, similarly, we can plug in cp dt for dh. And so ds is going to equal cp dt over t minus, and once again, we can plug in r. This time we can plug in, so we want it in terms of p. And so what we can do is we can say v over t is equal to r over p. So minus r dp over p. So last step is we are going to say that delta S is equal to the integral from T1 to T2 of CV dt over T plus R times the integral from V1 to V2 of dV over V. So what do we end up getting? Actually, let me plug in over here and then I'll put it all together at the end. So over here, delta S is going to be equal to the integral from T1 to T2 of Cp dt over T minus R from P1 to P2 of dP over P. Well, these pieces should be pretty clear. So this piece right here is going to be R times the natural log of V2 over V1. And this piece right here is going to be R times the natural log of P2 over P1. Okay. Now, what we're getting at is how do you use the tables for ideal gases to get at delta S? So now for this integral right here, what ends up happening is we end up using the ideal gas tables. So we have to use the ideal gas tables for this. So delta S is going to be equal to S degree 2. So this degree symbol is just used for reference in the ideal gas tables, and we'll talk momentarily about what that means. So bear with me on this for a second. So S degree 2 minus S degree 1 plus R ln V2 over V1. And so we can also approximate it using pressure relations. So delta S is going to equal S degree 2 minus S degree 1 minus R times the ln, the natural log of P2 over P1. Okay, and so what is this S degree 2 and this S degree 1? So let us talk about this on a new sheet. So we're going to use the tables. So this is going to be ideal gas. Okay, so for example, S2 is going to be equal to the integral from some reference temperature. So this is how it's computed in the table. From some reference temperature to our temperature, our final temperature, of Cp over T dt. So that's what they mean in the tables. Now, here's the thing. When you're integrating, you're going to end up with natural log of T2 over T1, for example, or T2 over our reference. And so when you take the difference here, you're going to have S2 minus S1 is going to be equal to, so you have the integral from the reference to T2 of Cp dt over T minus the integral from your reference to your initial temperature, Cp dt over T. So these reference temperatures are going to cancel out, and you'll get the true difference comparing T2 and T1 ultimately. So when Cv and Cp are constant, you get delta S is equal to Cv times the natural log, so that's a subscript V, of T2 over T1 plus R times the natural log of V2 over V1. And then you also get delta S is Cp times the natural log of T2 over T1 minus R times the natural log of P2 over P1. So this is another way you could compute it if you have a constant or close enough to a constant specific heat capacity in the process without looking it up in the tables. So these S with the degree symbols are looked up in the tables for ideal gases, or you could potentially use these relations, which I'm sorry are a little messy here. But let's go ahead and do an example problem together to try this out. So this is number 17 in your book for chapter 6. We have argon in a piston cylinder assembly is compressed from state 1, where the initial temperature is 300 Kelvin, the volume is 1 cubic meter, to state 2, where the final temperature is 200 Kelvin. If the change in specific entropy, so our delta S, is minus 0.27 kilojoules per kilogram Kelvin, determine the final volume in cubic meters. And so we're going to assume the ideal gas model with K equal to 1.67. So let's begin just by jotting down our givens. So given T1 is 300 Kelvin, V1 is 1 cubic meter, T2 is 200 Kelvin, and K is 1.67. And that's going to be constant in this process. And delta S is minus 0.27 kilojoules per kilogram Kelvin. So what is K? See if you can remember what K is. Take a moment, try to remember. All right, well, K is the ratio of Cp over Cv. And that's from equation 3.46 in your book. And so if you recall, Cv is defined as R divided by K minus 1. And we're tasked with finding V2. So let's begin looking at delta S, our equation for delta S. So delta S is equal to Cv times the natural log of T2 over T1 plus R times the natural log of V2 over V1. Now, we have R times the natural log of V2 over V1 is equal to delta S minus CV ln T2 over T1. And remember, our goal here is to find V2. So I'm trying to solve for V2. And little specific V2 over specific V1, it's going to be the same as the macroscopic extensive big V2 over big V1. Because it's going to be the same ratio whether they're meters cubed per kilogram, because this is a constant, it's a constant mass process, a control mass problem. And so the masses would cancel out anyway, so it's going to be the same ratio. So V2 is going to equal V1 times the exponential, so e to the power, that's what this means. I'm just writing it as a function so that it's easier to see since we have a lot going on in the exponential itself, times of delta S minus CV times the natural log of T2 over T1. And this is going to be divided by R. Okay, I'm just going to open up the new page. Now, we know that we can look up R, so the gas constant for argon is going to be 0.2082 kilojoules per kilogram Kelvin. And CV is going to be R over K minus 1. And so that's going to be 0.2082 divided by 1.67 minus 1. And this is still going to be in kilojoules per kilogram Kelvin. And that is going to give us a CV of 0.3107 kilojoules per kilogram Kelvin. Okay, now we can just plug all of this in. So V2 is going to equal V1, so 1 meter cubed, times the exponential of our delta S, which was given to us as minus 0.27, and that's in kilojoules per kilogram Kelvin, which is going to be the same units then as CV. So I'm just going to not write the units in right yet. So that's going to be 0.3107, okay, kilojoules per kilogram Kelvin, kilojoules per kilogram Kelvin, times the natural log. And this is just a ratio within the natural log of T2 over T1, which is going to be 200 over 300, or just 2/3, divided by R, which is going to be 0.2082 kilojoules per kilogram Kelvin. So we have the same units in the numerator as the denominator. So the units cancel out. So you should always check to make sure that when you have an exponent, anything that you have raised to the power that you're raising something to should always be dimensionless. So that's a good check. So this is a dimensionless quantity. And so we end up with our final volume is going to be half a cubic meter. All right, so before we finish for the day, this is the last problem we're going through. I just want to pull up the table so everyone's on the same page of what to look for when you're looking at entropy for ideal gases. So I'm just going to scroll down to the ideal gas tables. Okay, and so you notice, so here this is just ideal gas properties of air, and you see you have the S with the degree symbol in kilojoules per kilogram Kelvin. Okay, so that's this column right here, because you have to have, it's comparing it at this final temperature here to some reference temperature. And it doesn't really matter what that reference temperature is, because it's the same for everything in this table, and you're taking the difference between the entropy at these endpoints. So they end up, that reference temperature ends up canceling itself out when you take the difference. Anyway, that's all I have for you today, and we will keep on going with our entropy balances next time. So see you then.